Right, so in this video, I'm going to work through a few enthalpy questions. There are three ways to calculate enthalpy change in A-level chemistry. I'm going to work through a few examples now. So this first one here, and this worksheet can be downloaded from the website as well. So calculate the enthalpy change of combustion of propane. Right, now it makes your life a lot easier if you draw the molecule, if you draw the displayed formula of the molecule, so you can see all the bonds really clearly. So this is the enthalpy change of combustion of propane. I'm sorry, my hydrogens are a bit messy. So when you combust propane, you react it with oxygen, and it's complete combustion, so you make carbon dioxide and you make water as well. Okay, so the first job is that we need to balance it. Right, so we've got 3 carbons, so that means we're going to make 3 carbon dioxides. So I'm going to draw another one, and I'm going to draw another one. 3 carbon dioxides, yeah? So we've got 3 carbons. We have got 8 hydrogens, so that means we're going to need 4 waters. Okay, so I'm going to squeeze in, it's going to be a bit of a squeeze, 4 waters. I'm going to put another one here, 4 waters. When you get faster at this, when you get better at this, you don't need to draw it as detailed as this. 4 waters. Okay, so how many oxygens are we going to need? So can you see on the right hand side that we've got 6, we've got 10 oxygens. So therefore we're going to need 5. So I'm just going to write 5 there. We're going to need 5 oxygens in order to have a balanced equation. All right, so that's the combustion of propane. Then what I would suggest you do is you draw a line down and you make 2 columns. So you have bonds broken on the left. So remember that in order to have this reaction to happen, all the bonds have to be broken, and then we have to make on the right, we need to make all the bonds. So there is another video on bond enthalpy if you'd like to find out a bit more information. So we're going to break every bond. So we're going to use a different colour here. We're going to break the CC bonds. It's a good idea to strike the bonds like that. So can you see we're breaking 2 carbon-carbon bonds. Then you've got to make sure you get the value, you copy the value carefully from the table, and the value is 347. So just copy it carefully from the table. And then we're going to break how many CHs? So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 CHs. Now, by drawing it out and keeping your work organized, then you won't make any silly mistakes. So 8 CHs, 8 times, make sure you get the right value. CH is 413. And then also you have got 5 double bond oxygens. So we're going to break 5 double bond oxygens, which is 5 times, make sure you get the right value, 497. Okay, now you total up that side, and you have a go at it as well, and it should come to 6483 when you add up that side of the equation. Okay, now let's look at the bonds made. So can you see we've got 1, 2, 3, 4, 5, 6. We've got 6 CO bonds. So the value for that is 6 times, make sure you get the right one, 805. We've got 6 CO bonds. And how many OHs? 1, 2, 3, 4, 5, 6, 7, 8. And we've got 8 OH bonds. So again, take the value carefully from the table. 8 OH, which is 463, and then you total up that side, and that side should come to 8534. Okay, now breaking bonds needs energy, endothermic. Making bonds releases energy, exothermic. So therefore your enthalpy change for this reaction is going to be 6483, and just tidy this line up a little bit, 6483 and minus 85, you just add them together. There is a video on this on bond enthalpy if you need some more information, and your answer should come out at minus 2051 kilojoules per mole. Don't forget your units, they're really, really important. Okay, that's the first example. Let's have a go at another example. So they've given you the equation here. Okay, so calculate the enthalpy change for the following reaction. But again, let's draw it out and then no silly mistakes are made. C2H4 is ethene. Okay, so ethene, so it's got a double bond. And then you're adding water. And then that is making, it's already balanced for you, so that's making life a little easier. And then it's making ethanol. And again, make sure you draw out every bond and then you don't make any mistakes. I would suggest pausing the video and having a go at yourself and seeing if we get the same answer. Okay, so bonds broken on the left and bonds made on the right. And the products, bonds made. So let's do it very organized. So we are breaking a CC bond. So a CC bond, and that needs how much energy? 612 kilojoules per mole. Breaking 4 CHs. So we've got 4 CHs, and that needs 4 times 413. And we're breaking 2 OHs. So that's 2 times 463. And then total that whole side up, and it should come to 3190. Okay, and the same, doing the same with the bonds made. So you've made 1 cc, and that has a value of here we go, 347. Okay, you've got 1, 2, 3, 4, 5 CHs. And if you keep your working out really well organized, then if you make a silly mistake, like you read the table wrong, then you'll still get the mark, some working out marks. 5 times 413. Then you've got a CO bond. Very easy to forget the CO bond. CO bond is 358. And then OH, the OH bond. And if you hadn't drawn this out, you might have forgotten these bonds. OH is 463. And then you total everything on that side, and it should come to minus 3233. And then your enthalpy change for this reaction is the bonds broken and the, it's minus because bonds made, positive because bonds broken and bonds made. And that should come to, on your calculator, minus 43 kilojoules per mole. Okay, so those 2 examples of bond enthalpy. Let's try when you measure enthalpy change. So when you measure enthalpy change with an experiment like this, upon complete combustion of hexane using a calorimeter, you've got initial temperature of the water, final temperature, specific heat capacity. This is when you need to use the expression Q equals mc delta T. Okay, so Q is the energy transferred to the water. M is the volume of water, the mass of water. Okay, well, it's a mass of water, but can you see the assumption that we're saying here? We're saying 1 gram of water equals 1 centimeter cubed. So the density of water is 1 gram per centimeter cubed. So the mass becomes the volume. So it's a mass of water, 250 grams. The specific heat capacity means that there is 4.18 joules of energy is needed to heat 1 gram of water by 1 Kelvin. And then delta T is the temperature change. So we need to calculate the temperature change here. So 24.9, take away 19.7, what does that equal? 5.2. Okay, now the temperature change needs to be in kelvins, but that's okay because 1 Kelvin is equivalent to 1 degree. Okay, so what we mean by that is, as you already know, 273 Kelvin is the same as 0 degrees. Okay, so if you go up by 1, if you go to 1 degree, then that is 274 Kelvin. Yeah, 2 degrees is 275 Kelvin. So because it's a temperature change, it's okay for us to use Kelvin rather than degrees. Now, can you see the units then nicely cancel out and your answer comes in joules? So when you multiply those together, you should get, your answer there should be 5434 joules. And like I said, you need to double check as well. So you work out the energy transferred first, then you work out the moles of hexane next. So the moles of hexane is going to be the mass of hexane over the relative molecular mass of hexane over the MR of hexane. And the MR of hexane is 86. So when you do mass over moles, you get your answer of 0.0131 moles. Okay, now finally for your enthalpy change, remember that enthalpy change is the units of enthalpy change is kilojoules per mole. Okay, so we need kilojoules. Okay, so therefore we need to divide this by 1,000, because then that will give us kilojoules. 5.434 kilojoules. Okay, so that goes on the top, 5.434 kilojoules, and then you divide it by moles. Remember that when you have mole to the -1, that means 1 over moles. Yeah, so kilojoules divided by moles, 0.0131, and that gives us our answer of 414.8. I mean, you could round it up to 415 kilojoules divided by moles. And then finally, you've not to forget that the temperature has increased. So when the temperature increases, that means that it is an exothermic reaction. So don't forget to put your minus in. Okay, so that's how you calculate enthalpy change through an experiment. We've got an example now of enthalpy cycles, Hess's Law. So we need to work out that calculation. We need to work out, the enthalpy change for the combustion of hydrazine. So therefore we need a cycle. You have been given formation data. So we've got the formation of hydrazine. So we're going to write plus 51 by the side. And that's forming from its elements in their standard states from nitrogen and hydrogen. You've been given the value for the formation of water, but you've got to be careful because it says 2 waters, so you're going to need to do minus 241 times 2 because you've got 2 waters. Now you haven't been given a value for oxygen and nitrogen because the standard enthalpy change of formation of an element from its element is 0. You can't form an element from an element, it's already an element. So those values are 0, and that's why they've not been included. Okay, you're going to apply Hess's law. This is the enthalpy change that we're trying to find. So we're starting here and ending there. We're trying to find that. So we need to go down the reactants and up the products. You can watch the enthalpy cycle video if you need more information. So the enthalpy change for this reaction is going to be down the reactants. The black arrow is going the wrong direction, so we need to change the sign. Don't change the sign here, you change the sign in your calculation. And this black arrow is going in the right direction, so that is good. Minus 241 times 2, and then when you add that up together, I think what you get minus 533 kilojoules per mole. And like I said, these are practice questions, and there are videos to fully explain. Let's just do one more practice question. And it says work out the enthalpy change of formation of butane, standard enthalpy change. So we need an equation first. Butane is a gas forming 1 mole of butane from its elements in their standard states. Then we need to balance. There are 4 carbons and there's 5 hydrogens. Okay, the data you've been given is combustion data. So all the arrows are going to go down, 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 down. When you combust carbon, you're going to make carbon dioxide. And there's 4 carbons. So don't forget to go 4 times minus 394. When you combust hydrogen, you're going to make water. And there are 5 hydrogens. So don't forget to go 5 times the hydrogen, which is minus 286. And then you combust butane, and that's got a value of minus 2877. And that is your enthalpy cycle. We're now going to apply Hess's law. That is equivalent to starting here, going down, going up, and that will give us the answer. So the enthalpy change for this reaction is going down the reactants. So we keep the signs, the black arrows are all going in the right direction. Just be careful you don't accidentally write something wrong. And 5 times minus 286, you keep those are exactly the same. But can you see the problem here is the black arrow's in the wrong direction, so we need to change it round. So we change the sign so it becomes positive, and when you total all that up together, it comes to minus 129 kilojoules per mole. I hope you got the right answer too, and like I said, there are further videos to explain, and this worksheet is on the website. Okay, thank you.